Okay, the first speaker of this afternoon is McLean from Stony Brook, and the title of his talk is Birational Calabi-Yau manifolds have the same small quantum products.
Okay. So, let me write down the title. Okay, so I'm going to just talk about this result. This is the result. I should just be clear what I mean by Calabi-Yau manifold. So by Calabi-Yau manifold, I mean a smooth projective variety with over C with C1 equals 0. Okay. And maybe I should abbreviate Calabi-Yau manifold by CYM like this as well. Okay, and then maybe I should just be clear what birational means. So birational means they just have a common codimension 0 subvariety. So definition two Calabi-Yau manifolds are birational. So let's call these manifolds X and X hat. So they're birational if there exists codimension greater than or equal to 1 subvarieties, say V in X, V hat in X hat, so that X minus V is algebraically isomorphic to X hat minus V hat. And an example of such a birational transform is the Atiyah flop. And then there's other examples, there's sort of more general ones. There's something called a simple flop, which is more general. And then there's something called an ordinary flop. And there's other ones like Mukai flop, etc. So I won't describe what these are. But I could just say a word about how at least I can explain what a Atiyah flop looks like topologically. If you have say a knot in like a 3 manifold, you can do surgeries. You cut out a little tube. The boundary of the tube is a torus, and then you apply some diffeomorphism of the torus. So you remove that tube, apply some diffeomorphism of the torus, and glue back that tube again. So there's like zero surgery where you take the torus, you think of it as a square, you rotate it by 90 degrees and glue it back in, and that's zero surgery. So a Atiyah flop is like a sort of complex version of zero surgery. So you have a complex 3 manifold, you have some P1 inside of it, and this P1 is, has some normal bundle, which is a direct sum of identical bundles. And then you sort of remove a small neighborhood, swap the 2 bundles, and glue back in, which is exactly like rotating this torus. So that's sort of a very topological description of what a Atiyah flop might look like. Okay. And then, ordinary simple flop is like you replace P1 with Pn. Ordinary flop is like a sort of family version of a simple flop. And Mukai is something sort of similar. Okay. So we have this fact that I will need to use. The codimension, the complex codimension of V and also V hat in X and X hat is greater than or equal to 2. So, these birational transforms can't look anything like, say, a blow-up. If I take a Calabi-Yau manifold and I blow it up at a point, suddenly there's some sort of, near that exceptional divisor, the C1 is non-zero. So this is saying you can't have something codimension 1, because if you have something sort of codimension 1, somehow the birational transform would sort of squash it. And if it squashes that, it sort of creates some C1, but we're assuming C1 is 0. Okay. So this implies H2 is the same. So you could look at H2 x z. This is naturally isomorphic to H2 x hat z. And similarly with H lower 2. Okay, just because you're doing something in complex codimension 2, it doesn't affect H2 in any way. Okay, so this sort of leads to a question. So what properties do birational Calabi-Yau manifolds have in common? So this question has sort of, there's many sort of properties that people have thought about. But I'm sort of mainly just interested in sort of topological things, or sort of things like quantum products, which are sort of deformations of topological invariants. So there's a theorem by Batoréo, which says, this is in 97, which says they have the same Betti numbers. Batoréo used a technique called p-adic integration to prove this. And later on, there was a technique by Kontsevich that used something called motivic integration to prove this. And if you use this idea of Kontsevich and you combine it with some work by Gillet and Sol, so if you add this, then you can prove that they have the same integral cohomology groups. Okay, now that's kind of surprising because, I said it's something like a TF flop, it's like surgery or something like this. And, usually if you do surgery in 3 manifolds, like real 3 manifolds, then, it changes the topology drastically. And here it's saying it does, at least the cohomology doesn't change. So it's a kind of surprising thing, really. Okay. So you might think, well, what other topological invariants are there? Well, you could look at, say, the cup product, and then so you have there's a fact which is that the cup products are not identical. So they can be different. So there are examples of 2 smooth projective varieties with different cup products, but they're birational to each other. However, there's this sort of conjecture by Morrison and also by Rouen. So Morrison conjectured this in dimension 3, and Rouen did all dimensions. And And the conjecture is their quantum products are the same. And at least when Rouen conjectured it, he meant big quantum product. So your quantum product is a sort of deformation of the cut product. So if you add these sorts of correction terms, then suddenly they become the same again. Up to some, I should say up to analytic continuation. So you might have some sort of power series, and you have to identify them in some way. Okay. So let me just tell you some results towards this conjecture. So Lee and Rouen proved this in dimension 3. And then a whole bunch of people, Iwao, Lee, Lin, Ku, Wang, in a bunch of papers from 2011 to 2014, proved this for ordinary flops. So true for ordinary flops. And they had to develop quite a lot of technology to do this, as ordinary flop is this generalization of this Atiyah flop. Okay. Yeah, I should also say there's a conjecture by Wang. Maybe I should say it's this Wang here. He sort of conjectured. Maybe I'll just say what the conjecture is. So he said, if you have two birational Calabi-Yaus, then he conjectured if you sort of simultaneously deform them very slightly, sort of generically, then maybe the birational transform is a composition of ordinary flops. And so if that conjecture was true, then this work would prove this conjecture here. Also, these people didn't just look at, so big quantum product sort of encodes all the genus 0 Gromov-Witten invariants. You could ask, what about higher genus ones? And I think some of these people also did some work towards identifying higher genus ones, although they didn't do everything. They did it for simple flops, I think. Okay. So maybe I should remind you what small... I'm going to remind you what small quantum cohomology is, and I'm also doing this because I want to fix some notation as well. So let me just remind people what small quantum cohomology is. Even if you know it very well, I'm fixing notation. So I'm going to just fix a Calabi-Yau manifold. So smooth projective variety with C1 is 0. And I'm going to fix a Kähler form on X. And I'm going to work over some field K. This could be a field of any characteristic. And then we have a Novikov ring over this field. So I'll write that as lambda xk. This is defined to be sort of power series. Like this. So I'm not just using the Novikov ring where the AI are real numbers. I'm using the sort of full, like the bigger Novikov ring where I remember the H2 class. And then I choose a basis. So the easiest way to define this is you choose a basis. So A1 to AK. This is a homogeneous basis for H the cohomology of xk, coefficients in k, and then we have a dual basis. So this is the dual basis in so with respect to the pairing, I'll just put AB here. So you have a pairing, and you just take the dual basis with respect to this non-degenerate pairing. And then we have quantum cohomology. So this is so as a module, this is just cohomology. And then we have some product, which I write as star. And then you just need to determine what the product is on these basis elements. Should be a beta somewhere, beta here. So this is just, this M is just the space of genus 0 curves, the number of genus 0 curves. U passing through the Poincare dual of A1, AI, AJ, and AM. So you just have this P1, this sort of holomorphic curve. This is U, and it's sort of passing through these cycles. Like this. Okay? Oh, and it's in class beta, so this is the class of U is beta here. So this is just me fixing notation. Okay. Okay, so here's the main theorem. So we have these two birational Calabi-Yau manifolds. And we have choose Kähler classes. Omega X forms, I mean Kähler forms. Omega X and omega X hat. And they need integral lifts, so admitting integral lifts. So remember, I identified these H2. We had these canonical isomorphisms between the second homology groups. So I'm just going to take that for granted, that identification. And, oh, yeah, so I need a, yeah, so recall H2x is H2x hat. So that means I can define the following Novikov ring. Actually, I could just write it here. So I'm going to call it lambda x hat k. And it's going to be like this, but I require that the I remove this condition and I put the minimum of omega x of AI omega x hat of AI goes to infinity. So if you think about it, this is the intersection of these two Novikov rings. Like this. And as I said, I've identified these H2 groups, so I can pair it like this. Okay, so then the main theorem is the following. Theorem. So there exists a graded lambda x hat. Okay, module. Algebra Z and algebra isomorphisms Z tensor So we have an isomorphism like this, and we also have an isomorphism like this for x hat. Okay. So why didn't I just say, oh, this is isomorphic to this? Well, the problem is that if you have two birational Calabi-Yau manifolds, the classes of these two forms probably never agree. In all examples I know of, they never agree. So these Novikov rings are sort of very different, and you have to somehow compare, two algebras over two different rings. So the way to compare them is to look at the intersection of these Novikov rings. In conjectures like by Rouen, they compare these things via analytic continuation. So they go, well, let's assume part of the, this product is defined using these sorts of power series, and the conjecture, say by Rouen or Morrison says, well, let's assume that part of the sort of appropriate parts of these power series converge, and then you can sort of identify them via these two groups, algebras, via some sort of analytic continuation. But I do something more basic. I just look at the intersection of the Novikov rings and just compare them like this, which is it's not quite as also this is not quite as explicit as you want. So so the conjecture by Rouen and Morrison says these groups are identified in some sort of natural way. And I'm pretty sure these isomorphisms do identify them in this natural way, although the paper I wrote doesn't prove that. Oh, maybe I should just put the archive number. Yeah. Okay. So so as a corollary, so I sort of recover maybe a weaker version of this result by Batoréo. So this implies x and x hat have the same cohomology groups just over a field, any field K. I didn't really think about other things like, what about Z4, Z over 4Z or something like this. Just fields. Okay. Okay, so now I'm going to talk about some of the methods. So what I was going to do now is I will give a kind of moral idea of the proof. which is sort of maybe the bit you should remember. And then I'll explain some of the details, sort of trying to realize this moral idea of the proof explicitly. So, yeah, so let's start with the moral idea of the proof. Okay, so the first thing we do is we choose a common affine subvariety between, so we have this birational morphism. So if you have a birational morphism, you can choose a common affine subvariety. So we choose a common affine subvariety. So A inside X, which I'm also going to think of as inside X hat as well. So I have A inside X and X hat. And then the idea is to use Hamiltonian Fleur cohomology. So the next thing we note is that quantum cohomology is isomorphic to Hamiltonian Fleur cohomology. So we have these Hamiltonians, and the good thing about Hamiltonian Fleur homology is you have quite a lot of flexibility. You know, somehow quantum cohomology is like Hamiltonian Fleur cohomology, where the Hamiltonian is identically zero. And now I can change this Hamiltonian, and my equations, my sort of Cauchy-Riemann equations, now have this sort of extra term, and this gives me some additional sort of wiggle room to do things. So what do I do? Well, OK, so here's the idea. So maybe I'll draw schematically what's going to happen. So I'm going to write X as a line, like this. And inside X, we have A, which is, I don't know what color this is. This is A. Let me put that below here, below or above. Let's put A above, like this. Okay. And over here, we have X hat. And inside X hat, we have the same affine variety A, so the same codimension 0 affine variety A. Oh yeah, I should have said A is dense. Sorry, it's a common dense, Zariski dense affine subvariety. So the complement of A is some divisor at infinity. So this little region here, this is some codimension 1 thing inside X and X hat. And then I choose some Hamiltonian, and I have freedom to choose whatever Hamiltonian I like. So I'm just going to choose a Hamiltonian which looks sort of like this. It's going to be small here, and then it's going to get really big, and then it's going to be constant here. And then I choose exactly the same Hamiltonian here. Okay? And now I'm going to do something that's wrong, but I want to lie for the sake of illustration. Okay? So what I'm going to do is I'm going to say, let's pretend we can ignore these constant orbits. Obviously, you cannot ignore these constant orbits. They contribute to the chain complex. However, I'm going to just pretend to ignore them for the moment. Okay? So I'm going to ignore constant orbits near x minus a and x hat minus a. Okay? So I'll put an explanation mark here just to tell you that this is wrong, but let's forget that for the moment. So let me draw another picture. So let me draw x and x hat and a hat as two-dimensional things. Like, so my schematic diagram is going to look like this. Here's x. Here's x hat. And inside x and x hat, I remember I have these subvarieties, v and v hat. So these are the varieties where the birational transform is ill-defined. And away from, these are codimension 4 complex codimension 2 subvarieties. And so here's, so I'm going to draw that in green. So it's some horribly singular thing, and it's v here, and here's v hat. So the v hat could look very different. It could have some sort of horrible singularity like this. But outside v and v hat, x and x hat are identical as varieties. And then away from v and v hat, I have this common affine subvariety, which I drew in this color. So we had a here and a here, like this. Okay. And then you look at what are the orbits of this Hamiltonian. So if you look at what the orbits are, there's some constant orbits here. And then there's some sort of orbits, non-trivial orbits here, and maybe some non-trivial orbits here, possibly some non-trivial orbits here as well. So there's sort of non-trivial orbits here, here, and here, maybe some constant orbits here. And so, let's draw some orbits. And I'm ignoring these, so I'm going to ignore this. So I'm going to ignore these orbits. I'm going to ignore these orbits. So I have two orbits, and they're inside A, inside some compact subset of A, like this. And then I have the same orbits here. So I sort of assume omega and omega hat are the omega x and omega x hat are the same on some, say, large compact subset of my affine variety. And so the Hamiltonian dynamics of these two Hamiltonians are identical. And then I have a sort of differential, so with Hamiltonian flow homology, you have a flow trajectory. And this is real codimension 4. So generically, this Hamiltonian flow trajectory avoids V. And therefore, you have an identical flow trajectory here. And the Hamiltonian flow groups are the same. And you can do the same thing with the Pants product. Okay? So as I said, the only thing that's wrong is that I'm ignoring these constant orbits, and these are essential. So, okay. So how can I ignore these orbits? How can I set things up so I can ignore these orbits? So it turns out the best way of doing that is not choosing one Hamiltonian, but choose a family of Hamiltonians and take a direct limit. So really, we should have a family of Hamiltonians, and we should take a direct limit where this goes higher and higher. So we should really take a direct limit here. And then what happens is, if I have some non-trivial orbit here, when I apply the continuation map, you can calculate that this will go down here. And you can somehow filter out the rest of the... there'll be something up here as well, but you can somehow ignore it. Anyway, this is all packaged in something called Symplectic Co Homology. So we package all of this together, and we use Symplectic Co Homology. Okay, so the tool we use is Symplectic Co Homology. Some people call it Symplectic Homology. Co Homology. So this was originally developed by people like Chilibach, Fleur, Hofer. There's a version by Viterbo, but that's not quite the version I'm thinking about. It's more in the spirit of Chilibach, Fleur, and Hofer. There's a paper by Chilibach and Wancha, which has sort of a similar thing. And then there's a paper by Joel Groman, which has an interesting version of this group, and Sarah Venkatesh and Umut Varul Gunesh. So they have some papers recently which sort of develop sort of a symplectic cohomology group which sort of looks a bit like this. Okay. So how do we define this? So I'm going to fix some symplectic manifold M omega. So this is M should be viewed as either X or X hat. So let's say C1 of omega is 0. It's a closed symplectic manifold. And I'm going to choose a compact, so closed subset of M. And then I can define symplectic cohomology as follows. So I'll write SH star K inside M. And this is defined to be limit as A plus goes to infinity, the limit as A minus goes to minus infinity, the direct limit with respect to H, and the usual ordering on Hamiltonians given by just the less than or equal to, and then we take Fleur cohomology of H. Oh, and then, well, there's no K here, so I have to put a K here. So we require that H restricted to K is less than 0. And where's this A plus and A minus come in? Well, we fix an action. This is an action window here. This is an action window. Okay. So this action, so what I'm doing is I'm taking a direct limit with respect to the Hamiltonians first, and then I'm widening the action window. And when you usually define Fleur cohomology, it's the other way around. You widen the action window first, and then you take the direct limit. And I'm saying you should do it the other way around, and these are things, this will enable me to ignore these orbits, because somehow when I get sufficiently high, well, again, this is not quite true. I have to take a more sophisticated filtration, but I can do something similar and somehow filter out these constant orbits. Okay. But at the very least, if I fix this action window and I take this direct, so K is some large compact subset of A. So K is some very large compact subset of A, and the Hamiltonian is negative on K, and it's going to plus infinity outside K. And if I fix this action window and I look at some orbit here, some forbidden orbit, I can look at the continuation map applied to this forbidden orbit, and it has to go here. So somehow I can sort of ignore these orbits because the continuation maps will will send these outer orbits to these inner orbits. Okay? Great. Okay, so now probably I'll just finish this talk by just stating some formal properties of symplectic cohomology. And then whenever I write down these formal properties, you should think of how they apply in this context here with this compact sets K, these large compact sets K, and these Hamiltonians. Okay, so first of all, this is an algebra. So it's an algebra. And it's an algebra over this Novikov ring. I'll write lambda mk. I'm thinking of the generators of Hamiltonian Fleur homology as one periodic orbits together with some sort of capping surface, some sort of homology class of capping surfaces. So that's how I get this Novikov ring here. And then we have another property, so if, say, K1 is contained in K2, then we have what we call a Viterbo transfer map. So there exists lambda m K algebra morphism like this, and it's functorial, so if you have 3, the composite 1 is a composition of the 2. Oh, actually, I should say one other technical comment. So I'm doing something bad. I feel like this is what I did in how I define this in my paper. But I feel like this is not really the right thing to do. And you should take the direct limit on the chain level, and so take some homotopy limit, and then take some inverse limit. And this is an inverse limit, and this is a direct limit. And it behaves better. So I recommend reading. I really like Umut Varel-Gunish's thesis. It has a very nice way of defining this group. And I recommend, if anyone's interested, to read his thesis. Okay. Oh yeah, the third property is, well, it's isomorphic to, 3. So it turns out if K is like really small, like say a little tiny ball, something say Hamiltonian displaceable, this group is 0. So it's not always isomorphic to quantum cohomology. However, if K is M, it is. So SH star, so when K is equal to M, so SH star M inside M, this is isomorphic to quantum cohomology. However, if you shrink K and you make it really tiny, then it goes to 0. It eventually becomes 0 if K is tiny. So it's kind of interesting to see what happens. If you take, say CP1, and then you sort of shrink K, so you can make K to be a very large disk inside CP1, and then shrink it to a tiny disk and see what happens to these groups. It's kind of a fun thing to do. Okay, so here's the next thing. Well, so here's another problem, which is, well, in these pictures here, I had these large compact sets K here. Oops. So I really want SH star K inside X hat and SH star K inside X to be isomorphic to quantum cohomology. Well, this axiom just says if K is M, it's isomorphic. So how do I shrink M slightly and still get something isomorphic to quantum cohomology? So this is axiom 4. So I have a definition first before I. Say a compact subset. So we say a subset. Let's call it B. Inside M is stably displaceable if there exists a Hamiltonian diffeomorphism phi from M cross T star S1 to itself, so that phi of B cross S1 intersect B cross S1 is the empty set. So so B may not even be topologically displaceable, but once I cross with S1, it's definitely topologically displaceable, because I can just grow S1 or shrink it, and it will be displaced of itself. However, it may not be displaceable sort of in the Hamiltonian sense. So maybe I should write down an example here before I write down the axiom. So here's a nice fact. So any codimension greater than or equal to 1 subvariety is stably displaceable. So a fun thing to do is prove that the hypersurface inside CPN is stably displaceable. But I claim any codimension 1 subvariety or higher codimension subvariety, however bad the singularities are, is stably displaceable. So here's my axiom. So if, here's my property, I mean. So if M minus K is stably displaceable, then this Viterbo transfer map SH star M inside M to SH star K inside M is an isomorphism. So this uses, I think this uses ideas by, I think Victor Ginsburg talked about stable displaceability and this kind of stuff, and I sort of used ideas by him, I think. Okay. Okay, so far I haven't used the Calabi-Yau property anywhere yet, really. And you need to use it because if I take a Calabi-Yau manifold and I blow it up at a point, the cohomology changes. And so I have to use it somewhere, and I haven't used it. So where do I use it? Well, okay, so here's one place where I use it. I use it in several places, but here's one place. So in the next two axioms, I use this. So I have a definition which relies on the fact that C1 is 0. So definition. An index-bounded Liouville subdomain D inside M is, well, so it's a Liouville subdomain. So it's a codimension 0 Liouville subdomain. If you don't know what that is, it's sort of basically a codimension 0 submanifold whose boundary is a contact manifold, basically. With Liouville form, so it has a Liouville form. Do I need to state what the Liouville form is? Yeah, form theta. So that the associated contact form, so theta restricted to the boundary of D, has only finitely many Rabe orbits of each index. So this is a very strong property. And this is the index is measured with respect to a choice of trivialization of, say, the canonical bundle of the Calabi-Yau manifold or the symplectic manifold. Okay. So we have this property, and so the next two axioms rely on this index boundedness, and so if D0 is contained in D1, is contained in M, are index bounded Liouville subdomains and d1 minus d0 is a trivial cobordism, Liouville cobordism, then the transfer map SH star d1 inside M to SH star d0 inside M is an isomorphism. So if I don't have index boundedness here, this is not true. So this is an isomorphism. So for instance, if I take a really large disk inside CP1 and a really small disk inside that large disk, then this Viterbo transfer map is 0. It's not an isomorphism. Okay. And then the last axiom is the one that the last property, sorry, not axiom, property. The last property is the one that enables us to ignore these orbits. So, so let's say V, C be a closed subset of M, be, let's say, stratified by codimension greater than or equal to 4, say, submanifolds, say, real submanifolds. So you should think of V as like this region where the birational transform is ill-defined. So V is inside X, or V hat is inside X hat. Okay. Let's see. Yeah, okay, so let J be an omega compatible almost complex structure so on M. And we need another form, so and omega hat J compatible symplectic form on M minus V. And is that all I need? Let's see. Okay, so then, oh yeah, so and let D inside M minus V be an index-bounded Liouville subdomain. So then SH star D inside M can be defined over the Novikov ring lambda omega omega hat k. So this is the intersection of the two Novikov rings, one with respect to omega, one with respect to omega hat, using Hamiltonians which are constant. So are actually constant, not just C2 small to a constant, but which are constant outside a small neighborhood of D. So i.e. we can ignore these orbits. So this implies that somehow this SH sort of only depends on, say, J and M minus V or something like this, and D. So if you put all these ingredients together, then you get the theorem. So you apply it to this context. So you look at the. Well, let me just say a few words. I've got 3 minutes. So let's go back to the proof of this theorem. So we have these birational Calabi-Yau manifolds, x and x hat. So these are my birational Calabi-Yaus. And I have v inside x and v hat inside x hat as before. So here's x. Here's x hat. And then inside here I have v and v hat as before. This is v hat. This is v. And now what do I do? So I had this common affine subvariety A. A. And what I do is I construct a really large index-bounded Liouville domain, which is common on A and which is identical on both copies of A. So I have a large D here. D. So D is my index-bounded Liouville domain. And I compute. So I use the axioms to show. So to compare. So they use the axioms, not axioms, properties. So use 1 to 6 to identify this with this. I should comment one thing. So this D is index bounded. So how do I prove that? So what I do is I take my affine variety A, and I take X and I sort of blow it up along various sort of subvarieties until the complement of A becomes a normal crossing divisor. And if I have a normal crossing divisor, I know exactly what the Rabe dynamics look like. And I can compute the indices explicitly of the Rabe orbits. And the indices, and because C1 is 0, I can just compute the indices of these Rabe orbits, and they depend on the sort of order of the canonical bundle along these exceptional divisors. And the order is always positive along these exceptional divisors. So the order of the canonical class is always positive along these exceptional divisors. And that enables me to prove this sort of index-bounded property for these Liouville domains. Okay, so I'll stop there.